Welcome to the module number 5, that is on verification in the course of optimization techniques for digital VLSI design. So, what we are expecting in this module? So, till module number 4, what we have basically seen? So, we have basically seen that we start with a specification and then we go for some kind of high level specification, formalizing in terms of some RTL languages or some hardware definition languages, so that you can have a specification represented in such a form that it can be implemented in hardware. Then we go for high level synthesis, then we go for 2 level or multi level Boolean optimization, that is gate level synthesis, and then we have placement routing, and finally in between we also have to plan our test, because all the devices to be fabricated are not free of faults, as we know, already discussed in module number 4 in entirety. But what are the issues of related to test? So, we do lot of test plannings also in the flow. Now, finally what? So, finally you have a chip which is fabricated, tested and sent to the market. Then what is the role verification is playing? So, you might have seen that basically at every stage VLSI design basically is a translation. First we have some specification which is written by some human as a human being, maybe in a non-technical language. Then you convert it into some kind of more formal representation. Then you define them in terms of hardware specification languages. Then you have register transfer level modeling. Then you have gate level modeling. Finally you lay it out and place and route. But it is actually the same representation of basically what you have thought, that what as I have given as a design intent, that is basically implemented in terms of a layout or in terms of transistors. Basically, so it has gone through different phases. Now, formal verification basically checks mainly that whether whatever I have intended in my specification is at a very abstract level, is exactly equivalent to what is being implemented at the transistor level. That means, if I wanted to design an adder, finally the transistor level implementation should do an addition, or it should implement an adder. Now, how can I do it? Very simple is that I apply all possible input cases and see whether at every point, at every stage of translation or changing of one way of representation to another maintains equivalence, that is, they have to give same outputs for every given input. But now, obviously, already many times we are discussing in the course that if your circuit is at least reasonably complex or at least having more than 10 inputs, everything will blow up if you are trying to give all possible input cases. And it is actually infeasible way of verifying or even testing anything. So, in case of verification, what we do, and we always use the term called formal verification. So, what do you mean by formal verification? There are some other ways also which we call simulation way of verification, but in this course we are restricting to formal verification. So, what do you mean by formal verification? In this case, we are not going to apply test patterns or input or what do I say that patterns or test cases to validate the equivalence. Rather, what we will do, we do it in a formal manner or in a mathematical manner. We will have a model for the system which will be a formal model, and then we will try to express our design intent or what we wanted to design in terms of some properties. And then we will do something called model checking. In other ways, we will try to verify formally whether the model adheres to these specifications which are in terms of some kind of formula, logical formulas. If it is verified, then it is mathematically true that basically your system or your system that is modeled is actually behaving properly with respect to the formulas you want to verify. And if there is some problems, it will actually give a counter example. That is very important, that if some of the state sequence of the model is not validating or is not satisfying that properties, it will give a counter example, which will allow you to find out what are the bugs and you can recover. So, that is the basic idea of formal verification. So, what we will cover in this module? So, first one will be a very basic, because you have to understand, because as I told you in this course we are first giving you the basics of CAD for VLSI and then you are building upon it. So, first we will be looking at LTL and CTL based verification. That is the core idea that for any kind of formal verification you should first understand what is LTL and CTL model checking. So, which we will be covering in this lecture. Then basically we will going into, as the course is on optimization, then we will try to see what are the problems with LTL and CTL based verification if you are handling a larger system. Then we will talk about how to verify large scale systems, what you have to do. Basically that is one of the core gist idea, in which case we will try to see basically how large scale systems can be model checked or formally verified. In view of that, we will see very important things like something called binary decision diagrams. Binary decision diagram is a way of handling large systems which models large systems by eliminating out your so called the redundancies. So, we will see about binary decision diagram based verification, which is also called symbolic model checking. Then binary decision diagram is an abstract is actually still it actually minimizes the state space representation by eliminating redundant variables. But in fact, but still it is at a bit level. Then we will basically see there is something called ADD based verification, that is arithmetic decision diagram or high level decision diagram based verification. That means what? We will not go to the bit level, we will rather go into the higher level of abstraction and try to verify the systems. Like we have already seen in case of test, basically when if you are going for the gate level, the complexity is high, but when you are going at the RTL level of testing, the complexity gets lowered down by high level abstraction. Similar things we will also see in the case of verification. Finally, basically as I told you, symbolic model checking is nothing but it is a part of when we are talking about large scale verification. Symbolic model checking is the way to do model checking for when you are using binary decision diagram. And finally, what we will see is that something called a bounded model checking. With the bounded model checking is something like we do not want to check the whole systems in the entirety. Maybe one path in the state based model can have 2 million states in that path, but maybe you do not want to model check that long. We want to just find out if any bugs exist or whether your property is verifiable within first 3 steps. So we can put a bound till what depth or up to what path length we have to search. So these steps are basically for your trying to use this model checking for large systems, which is the main motto of this course. Okay, so let us, as this is the preliminary lecture, which you can also find in lot of textbooks on formal verification or many CAD for VLSI course covers this lecture, but it will be quite elaborate in that cases, but in our lecture today we will try to give you everything in a nutshell so that you get it is a prerequisite. So what is the difference between verification and test? I have already been telling you, but you can look at this slide. What it says, verification verifies correctness of the design. It checks if the design meets the specification or the intent. But test basically means it is basically a device has been fabricated which is already formally verified to be working proper, then only you fabricate it whether in the fabrication process any defect has gone in. So verification means it is prefabrication, testing means is post fabrication. Basically mostly verification are done formally, and in testing basically it is slightly different. You have the devices there, you put some test patterns and you verify and you determine whether there is any defect or not. But there are actually testing is a 2-stage process, already we have seen. One is test pattern generation or test planning, that given a circuit what are the inputs you have to give, then at what timing you have to give, all these plannings we have seen in the last module is called the test planning. So that will give you the test patterns, and once it is fabricated you have to apply those test patterns. So there are 2 cases basically, one is determining the test patterns and one is final application. Okay, so testing is a club, but practically speaking quote unquote testing means the patterns are there, the device is there, you physically apply it. But again verification is generally done once prior to manufacturing. That is, verification means our design is there, you have implemented based on terms of this design. Before implementation in terms of hardware you verify whether it formally adheres to your design intent. So it is generally done once. But testing actually, as I tell you, 2 steps are there. One is test pattern generation, that is again done once because you have determined what are the test patterns to be generated which will be finally applied, but while applying the test pattern it has to be done for every device. So basically in a nutshell, if I have to say what is the difference between verification and test, so verification actually tries to find out whatever you have designed is formally correct or it is adhering to the design intent, and test basically is something like it is a procedure in which case the device already has been fabricated because it was already proved to be working, proved to be formally verified, then the device has been fabricated based on that guarantee, then whether any defect has come in the fabrication stage, that is not at all by any error of the designer, something has gone in. So we want to find out whether that any defect is there or not, so we apply test pattern and we have to do it for all the devices. So therefore basically it is called there is a test. So that is the slight difference between verification and test. So as I told you, verification can be of many types, like one is something called a simulation based verification which we do not do at all, means I should not say, but many cases is applicable, but generally we are not able to give all kinds of all possible test patterns to verify or all possible test cases, I should say. I should not call the test patterns basically. In terms of verification we should basically call it input cases, like in your 101 CS 101 type of courses like C language courses, what will happen basically, you write a C code, then your invigilator or your teaching assistants come and he or she runs your C code with some test cases. So that is some kind of a verification. But in that case, it is only bounded to be verified by the input cases he or she is trying, but it cannot be mathematically proved. That is what you are doing in your labs, 101 labs, basically that is something called simulation based verification. But it is not possible because to make it an exhaustive kind of verification is totally out of question. So it is exponential in the number of stage variables, nobody even tries. And also so even if you are using a simulation based verification, the input size is less, and also we do not know what is the quality of inputs of the test cases. So there are a lot of issues. But whenever we are doing a formal verification, the idea is that you are modeling it, and you are modeling what are you expecting in terms of formulas, and then you are going to model check formally, and if your model checking tells that okay, the formula is valid on this model, then you know that the model does not have any bugs with respect to the formulas. So in that case, it is a guarantee that your system is going to obey the design intent which was represented in terms of formula. So that is why I say something called non-exhaustive simulation. So non-exhaustive simulation means generally some people call non-exhaustive simulation based verification, which is mainly used in many of the industries, but in which case there is a group of design engineers who design it, and there is a group of test engineers or verification engineers who, instead of doing it formally, basically they design a lot of good test cases, and then you find out whether there are any bugs there or not. But in that case, test generation is also a lot of human intervention is required, and lot of experience is required, and sometimes we may not cover all possible error cases or bugs, so lot of issues. So in this course, and mostly basically people are more formally oriented or more oriented towards developing something called formal verification. I think you already know about the Pentium bug. There was some bug in a Apollo spaceship, in which case it happened that people have all of them had basically done something called a non-formal verification, that is simulation based verification or non-exhaustive simulation based verification. They were also very intelligent people, because designers of Pentium, designers of Apollo spaceship, so they are all very intelligent people, but still they had missed out on some parts on the writing good quality test cases. They might have missed 1 or 2 test cases which led to the bugs when the system was deployed in the market or in the system, and one led to the catastrophic end of the spaceship. And in case of Pentium bug, the issue was more of finance, because all the chips which had bugs were brought in from the market and they have to be given new chips, and all the market reputation came down. Testing and verification, here is a difference. Again, I want to highlight it. When they are saying the design is verified to be correct, then basically it assumes that the design has been mathematically checked, and the testing is not going to again look at the bug which is coming because of the design engineer. It is looking only for the defects which has been introduced by manufacturing process. So if your design has a problem, testing can never find it out. So therefore, Pentium and the Apollo incidents I have told you, they were mainly because of non-exhaustive simulation problem, based verification problem. So what people are saying, basically there is something called a formal verification method. So in this case, there is a finite state machine model, or any model you can use the FSM model, Buki automata, then also we will see a BDD based model, and so many different type of models can be there, but it is a formal model of your system. This has to be done manually, and there are a lot of issues. You can ask me that who does this model, how do you know the modeling is proper or not. Then there is something called specification, in which case you write your design intent in terms of some kind of specification formula. Then there is a verification tool which mathematically checks whether this model obeys this specification or not. If everything is right, you will get okay, otherwise you will get an error trace. Now I will answer your question, that if I make some model mistake in the modeling, then but specification is generally very simple, as you will quickly see that it is very difficult to make errors there, because specification is simple to write your design intent. Like for example, I say if I request a job to the printer, in some time I should get a reply. So the specification will be very simple: request, imply, in future grant. So the specification writings are smaller compared to the modeling, but modeling a printer, you can understand, it's a complex task. So either to get a okay signal, generally this has to be correct as well as the modeling has to be correct. Modeling means basically this is a printer physical implementation, this has to be translated into a model. Rather basically the idea is that people have thought of some kind of model and then they have designed the printer, but generally it may not happen all the time. So generally people have designed it in a different ad hoc manner. I mean, I am just quote unquote saying, do not exactly go by the words, but if you say that very specific way of designing systems is that you should first have a model, then you have to implement it, and then only you can go for the implementation. But generally it does not happen in the practical scenario like that. People generally manufacture or design some systems, and then people go for formal modeling when they have to go for a model checking. So now the idea is that even if there is an error in the model, I may have done some modeling error. The system may be proper, but the modeling error may be there, but still you are not going to get an OK signal, you are going to get an error trace. Then you have to find out whether what is the problem there. So you will find out that okay, this part has a implementation problem. Then okay, then you will quickly say that see your printer implementation, this is an implementation problem. Then if it is an implementation problem, very good, they will repair it or debug it for the future use, but sometimes they may also say no, see, our implementation was proper, only the way you have modeled has a problem. You have not captured in a proper modeling, you could not capture the modeling in a proper manner. This is very similar to your course on automata theory. Sometimes your teacher gives you that there is a string, write a DFA for that. So okay, many times you make an error in representing in a proper model of a DFA. But then basically in this case what happened, then you say this is a bug. So basically this bug may be either in the model or the system, implemented system, but anyway you will find out what the error is. It is very rare that even if you make an error over there, still you are going to get an OK signal. It is a rare case, very rare case. So generally either the system has a bug, you will find out, or whether the system does not have a bug, but this finite state machine model representation something might have come in, then you can do. Third picture, even if you write a specification wrong, then also you may still get a bug, then you can find out that okay, everything is fine, the specification was not mentioned properly. So in fact everywhere going wrong is a very straight probability. So therefore we have a very nice way, it is expected that you get a fine good modeling, formal model of the system, you write a specification, then you automatically give it to the model checker, no human intervention, then you find out okay fine, otherwise you are going to get an error trace. So error trace will tell you where there is a problem. So in that case you find out what is the problem in the system that is designed, and then you try to rectify. We will take lot of practical examples today to see it. Now before as we were saying that we will go for formal verification, so we are just going to quickly cover some logics which you have already done in your theoretical foundation of computer science. So what is a propositional logic? Okay, so if you look at it, so propositional logic means I have statements like I qualified in GATE exam 2010, I prepared well, I got a non-scholarship seat in Guwahati. So if you are making some direct assertions, this is true, this is bad, this is good, something like it comes as a propositional logic. What is predicate logic? Predicate logic means you have quantification, like Wx, x gets a fail grade, some variable you have, Rx, x is working hard. Now there is something called for all and there exists. So if I write for all x, Rx imply Ux. What does it mean? That means for all who work hard imply that x is So in fact basically I should not call it as a fail grade, it is a reverse way of writing it. I should write it as will x get good grade. Okay. So basically Wx means x gets a good grade. So basically it means there is nothing wrong in saying Wx x gets fail grade. These are predicate logic. But if I am writing this is sometimes making this means thing non-behavioral basically, means not practical. So what it is saying, for all x, Rx imply Ux means for all those who is working hard will get a fail grade. There is no problem in this mathematical representation of predicate logic, but it is not a practical way of handling in our real life. That means this is not a correct when you apply to our real life, because who works hard generally will get good grades. So basically I can write, but mathematically speaking there is no problem. So predicate logic means that there can be a for all and there can be an existential quantifiers. So it is saying that for all Rx, that is means for all x, Rx, that is all who is working hard, imply Ux. That means we will get a good grade. Means fail grade means it is a non something very unnatural. So that way you can write, but idea is that propositional logic means there is no quantification, it is a direct hit, like I get good marks, you get bad marks, something like that, and predicate logic means you can have quantification. Now there is something called temporal logic, which is very important in today's context, because we want to find temporal, these are all static. Because I prepared well, all those things, like I get good marks, whoever reads well will get a good mark, they are all statically true or statically valid or invalid, whatever you want to say. But temporal logic means it is not statically true or false in a model. It will depend, like if there is number of states in a system, in one state it may be true, other state it may be false. So that is actually called temporal logic, that is what use temporal. Some examples: I am always happy, that means there is something which is valid in all states. I will be eventually happy, that means there is some future state where I will be happy. I will be happy until I do something good. I am happy. So I am happy basically you can say means basically some kind of a propositional logic. But any temporal logic is a superset you can think, because means if you say that something is true in all these states, so that is nothing but your propositional logic. But temporal logic means it can change over states, but even if it does not change over states, still it is valid. So temporal logic you can think as a bigger set. But anyway, we are not going into all these subset superset relations now, but temporal logic you have to understand something which can change over time, that is the idea. And in the worst case, something may not be changing over time, it can be valid in all the states or invalid in all the states. That will also come under temporal logic. So it is saying I am always happy, eventually happy, until. So there is something which will be true in some state and true in false in some state. So that is actually called the temporal property. And most of our formulas we will be writing today will be under temporal logic. There are two types of very important temporal logic. One is called branching and linear time. So linear time, basically you can thinks of time as a set of paths, where a path is a sequence of time instants. So this is linear time, that is linear time temporal logic. We might have heard the name always many times. So basically it is depending on some kind of paths. And branching time logic basically represents a tree, and there can be different paths branching out of it. So we will try to cover this, but I mean I do not want to go into all these details, that which is a superset, which is a subset. Basically there is something called LTL, and there is something called CTL, which we will try to see, mainly we will try to see CTL properties today, and basically which will give, because but you cannot say that one is the superset of other, because there is something which cannot be written in CTL, and there can be something which cannot be written in LTL, and all these things are there. But for that you need to know all details about CTL and LTL model checking. So you can take any standard textbook on CAD for VLSI or verification, you will be finding it. But what I am trying to give, this course basically is an optimization part of verification. So CTL will also require optimization, LTL also will require verification. So in our case basically we will be mainly looking at your CTL based model checking, and so that I mean basically there all other techniques of optimization we will be talking about for CTL will also be applicable for LTL or any other model checking you apply. So unnecessarily means in this course, if we are going to teach you about LTL, CTL, then which is the superset of other, and what is possible in what and what is not possible in this thing, it will actually divert it, and it is mainly available in any kind of CAD for VLSI course. There is something called CTL star, which basically takes care of both LTL and CTL model checking. It is a superset and it can handle both. So I mean those things you can find out in the textbook, any kind of a textbook. But okay, so anyway, but just some formal definitions I have given you: proposition logic, predicate logic, temporal logic, what is branching time, what is linear time, and what is branching time. All those definitions basically in a gist I have given you. But mainly we will be diving into depth for CTL model checking and try to find out that what are the issues there in terms of complexity, so that we can handle it in future, because our course mainly is focusing on complexity issues. So there are some temporal operators, like there exists an x, phi x, that means there is something which holds in the next state. F phi, that means this formula phi is a temporal formula which eventually holds. F means in future. Global means globally, every state it should hold. And phi until psi, that means that phi holds until psi holds. I will take all examples and elaborate it carefully and in details. But some temporal operators are next state, future, globally, and until. So we will start taking examples. Next state phi. So in this case you can say that in next state phi is true. So you can write in state xj this property is true. Okay, the temporal property is true, and in next state phi is true. So in this state I can write this one is true. So this is the mathematical array. Sj satisfies Sj satisfies this formula, because in next state from Sj this one, x means next state. In future. So here I am writing in future phi is true. That means this is be holding in this state as well as be holding in this state, because there exists some state in future where phi is true. So I can write in state S0 this formula is true, this is true, this is true, this is true. Here also I can write this is true, because present state is also future. That one thing you have to write. In state Sk also I can write in future phi is true, because present is also a kind of future. Globally, so in this globally means some states, from some state where globally in all other states from the path starting from that node, because basically we are going for branching time logic. So like for example, this state satisfies all these formulas, because in all these states downwards trace phi is true. So I can write from all these states globally phi is true, because in all states phi is true. Of course this S0 is not satisfying this formula, because in the state S0 itself phi is not true. So globally means from the starting state as well as all states is actually having this, whatever formula should hold all these states. Important one is this one, that is basically psi until phi, that until operator, that is very important. So what it says, psi should hold until phi holds. That means phi will keep on holding at a state from where psi is going to hold. That means what it says, psi until phi. So until phi, whenever phi is there, this means something you are very safe. But whenever phi goes off, psi should take it through. That is psi until phi. So until phi, everywhere till phi is there, no problem. Whenever phi stops, psi should take over. So actually this state satisfies this. But of course, you can say that this state satisfies because from here psi is 555 and from where phi dies down this one takes over. For in this case you can say that is not true because it is not satisfied in S naught because here phi is not true, still psi is not taking over. So therefore in this state is not satisfiable. That means you can think something like this is a safety property kind. So from whenever the safety property or some good property starts holding, then phi need not be there. But still then he has to, or this guy has to give a backup kind of a thing. So just to remember this. But psi until phi is something represent. This is the mathematical formula which says that there exists a k, some k is there where basically psi is holding. And before that, for all j less than equal to k, for all j less than equal to k, your phi should hold. So basically in Sj it will be true because there exists a k where psi is true, and at any other k like this and this which is less than equal to this basically k, your psi is holding, but S0 will not satisfy this. Okay, so you can say Sj, Sji plus 1 all satisfy this temporal property. Now we will take slightly more combinations, like in this case it is saying P imply in future Q. That means what? One very important thing I should tell you, you might have done this in logic but you still should remember. So what does A imply B means? Means if A is true, B has to be true, or there is something called, that is obvious, but there is something called vacuous business here. So if some place A is false, in that case B becomes vacuously true, that has to be remembered. So A imply B means basically not A or B. So if some place basically A is false but B is true, in that case we call it a vacuous truth basically. Means if it implies that if A is true then this should happen. If some A itself is false, they assume it to be vacuously true. But otherwise if A is true then B has to be true, otherwise the property is not holding. So that is one thing you have to keep in mind. So what it is saying? It is saying P implies in future Q. So here P is true, which will imply that in future Q is going to be true. So it is true and this state. But if you sometimes tell me that whether at S0 what is the case, but in S0 you can see that P itself is not true, but in future Q is true. So that means it is vacuously true in this state. So that you have to just keep a thing in mind, that what is mean by vacuous truth. Here it is saying, next one is saying P imply and Q until R. So let us see in the state S0. So in this state S0, so let me just zoom this up for you. So in this case what it is saying, so P and Q until R. So Q until R means it should be Q, Q, Q. So from this is Q, Q, sorry. So that is Q, Q, Q and Q, after that R should start holding. And but in all these states P should be true. So if you look at it, it is holding here. You can see all these states P is holding, and the other part, that is AND part of it, that is Q, Q, and whenever Q stops R should start holding. So this state sequence actually satisfies this property. Now this is something called CTL, this computational tree logic. As I told you, apart LTL is also another way of serving the same purpose, but again the power of LTL and CTL model checking is slightly different, but in this course we are not trying to go into all those aspects. Basically we are trying to see CTL and what are the complexity involved here, so that we can try to resolve those complexity issues and go for optimizing verification tools for large scale circuits. So what is the syntax of CTL? So CTL formula, that is your formulas which you have to write to design, to express your design intent. So there should be a lot of atomic propositions. So what are atomic propositions? I send a request, it is raining, he is a good boy, something like that. Then there are some path quantifiers, because as I have told you, CTL means there are a lot of paths from the root node, there can be a lot of path branching time. So you can say that A means over all paths and E means there exists a path. So there can be two ways of representing this, all paths or there exists a path, because the branching time logic. Then propositional logic operators like AND or NOT will obviously be there, and temporal operators like we have seen next state, future, globally, until. So basically these are the syntax of CTL. Then there are some CTL formulas, like for example true, false, and or not, imply, everything will be there. Like in this case it says there exists a path where globally, in all paths globally. So we can have path quantification over here, because from a tree we will have lot of nodes. So from a root we will have lot of paths. So you have to select any or two of them, right? For some examples are given over here. So it is saying AF, AGF1 means always globally, that is in all paths globally F1 holds. EG means, that means there is a lot of paths from in all paths globally F1 should be holding. EF G1, that means there exists at least one path from here, and in that path specifically everywhere F1 holds. AF1, AF F1, what does it mean? That means there exists a path, sorry, AF means for all paths in future F1 holds. That means for all any path you take, at least one path will be there where in future, sorry, all paths, these are all paths. So in all paths, actually in a future node, at all the paths basically F1 will hold. There exists EF F1 means among all the paths there is at least one path where in future F1 is going to hold. There are some CTL formulas. Okay, there are something called these are called well formed CTL formulas. There is something called non well formed CTL formulas, because there are a lot of, means if you have to actually adhere to this paradigm to write these formulas. But what is in this part and what is not a well formed CTL formula, please refer to any standard textbooks on model checking, you will be finding out the idea. Then basically, as I told you, there is a model on which you will be verifying this formula. So basically there is a Kripke structure, we name it like an automata, we call it the Kripke structure, with a temporal structure where you have the set of states, there should be a transition relations. Along with that there is something called a leveling function, that is very important, like just like any finite state machine you will have state and transitions, but along with them there is something called a leveling transition, that each of the state some propositional, that is your basically your what do I say, these basically atomic propositions like it's raining, it's good, heating on, such thing, heating etc. has to be labeled. That means it is true, all these atomic formulas are true in that state. So basically we always try to write it in atomic form, because after that you can use the logical operations or operators. Like for example, I write it's raining and the breeze is there. So I will write P comma Q, means P means it is raining and Q means weather is good. So I can write P comma Q, because we do not want to write a ampersand etc. inside the states. So we are in the labeling over the states. That means in a state whatever propositional or atomic formulas are true, you can directly label it. So it is a Kripke structure is similar to a state transition diagram. So all state must have an outgoing edge. Each edge is labeled with one of the elements of the power set of the atomic propositions. That means there will be some edges, but here what will be the power set, that means any one of any super subset of these atomic propositions which will be true in this state has to be labeled. Example. So if you can look at it, it's a Kripke structure, and P, Q and R are some kind of atomic propositions. So in state S0, these two are true, in S1 P and Q are true, S2 R is true, and so forth. So that is what is written over here, that is the labeling function. So S is the set of states, S0, S1, S2 and S3, transitions are written over here, and it shows L of S0 P, Q, R, that means in S0 these are the three propositions which are true, that is P, Q and R are true in this case. S2 only R is true, that means in this state P and Q are false. Now illustration of basic CTL temporal operators, we will start with this, because and I want to say that in this, you can see this is some kind of a model M and we will see what are true here. So in this case you see this is state S, S0, and whichever atomic properties are true are labeled over here. So P is true, here Q and Q is true over here. So we can write in M S0 it satisfies P, that means it S0 P is true. That is the way of writing the properties. Like M S, this is the property, and we say that in M S0 is true. That is how we write. M S1 not P is, this one is S1 not P is true, because P is true over here and here only Q is true. So we can write at M S1 P is basically not P is true. So this is valid in state S1, because we are not having a P over here. Had P been there, we would have also written P in this state. So that is how we do it. It's very simple. Very simple. If you look at it, it is something saying that P, Q and there. So in this S0, S1 you can say both P and Q are true, and this property P and Q holds in state S1. Similarly S2 you can write P or Q, because Q is true over here, P is false. So this is an OR. So in S2 will satisfy this formula, CTL formula, because as I told you P or Q is also a CTL formula. Now slightly we bring the temporal business exactly into picture. So you can see all path next state Q. From here you can see that there are three paths, 1, 2 and 3, and all these three paths from S0 next state, X means next state, Q is true. So Q is true over here, Q is true over here, Q is true over here, done. So S0 will satisfy this CTL property. Next one, there exists a path. So EXP, that means there exists at least one path, like from here to here, where from here the next state is S1, where basically P is true. But you can see in this path and this path next state P does not hold, but still the formula is satisfiable, because it is not A, it is E. E means there exists at least a path here where in the next state P is going to be true. So this formula is satisfied in state S0. Next one, what it is saying? It is saying that S0 globally Q. That means from S0, if I take any paths in all these states, Q has to be true. So if you take a state from here, you go over here, you keep on looping. So Q is true over here, Q is true over, is fine. So I take another path from here, I will go to Q is true, and from again Q I can loop over here. If I take another path this way, everywhere Q is true. So therefore from state is not all paths globally, from here whatever paths you take, and in all the states in that path Q holds. Basically this is the mathematical definition, you can read it, this part is the mathematical definition, you can read it, but I am just giving you the literal meaning. Okay. So in this case they are having a formula called EG phi. So what it says, that means you can zoom it. So EG phi means there exists at least a path where globally some phi statement is true. So if I can say that if I make it as a P, so let me make it instead of phi, general value, I make it P. So now you see, so it is true over state S0 because there exists a path from here loop where globally P is true. So P is true over here, P is true. But I cannot write there exists for all paths AG, I cannot, this is satisfied, but I cannot write AG. So I cannot write AG, if I write AG it will be not true. So if I write AG, what is going to happen? So AG means for all paths globally P is true, but there is one path over here, or there is at least one path, like one path from here to here P is not true. So it is really not true. That is how AG phi P will not be satisfied at S0, but EG P will be satisfied. But I can write something like for all paths in future Q is true, that is holding in state S0. Why? Because see in this case in future, so in future Q is there, right? So here state will be there, in future Q is going to be true. There is a path over here, in future Q is going to be true. There is a path here where in future Q is going to be true. So future means what? It may be for all paths basically at present. Basically I can also slightly modify this, then also it will be holding. So if I make it as right. So you can see here, so it says that in all paths in future Q is true. So here Q is false, but if you take a path here in future Q is going to be true. In this path again Q is going to be true in future. Again in this path, another path you take, Q is going to be true in future. Even if nothing is true over here, that also will satisfy this, because in this case P not true, because I need Q to be true, in this path not true, but here actually Q will become true. Even I think it will start even hold if I even destroy this, because there is a path here where both P and Q are true, that is in future, not globally. He is saying that from all paths here in future Q is going to hold, and in fact that is holding over state S1. Okay. So these are very simple way of actually representing some of the formulas, and I am giving some diagrams which are telling you where it holds and where it does not. This is again representation of P until Q. So in all paths from state S0, P until Q. So P holds, P stops holding, Q starts. Here P holds, here P holds, P stops, Q starts taking over. So in that path also. So here all the three paths you take, P is holding, but wherever P stops holding, Q takes over. So it is true over here. In this case, if you look at a slightly modified diagram, so in this case if you see P stops holding, but Q does not hold over here. So in this path P until Q is not satisfied. Similarly P here, P does not hold here, Q does not start its job. So in these two paths, basically this path and this path, P until Q does not hold. But this formula, if you see, it is saying E, there exists at least one path where P until Q should hold, and actually it is happening in this case. P, whenever P stops, Q takes over. So in this case, it is an existential, it is actually satisfied over here. Now how a model checking is basically done. So first is modeling. So like these things basically, as I told you, this structure you are looking at it, the Kripke structure, this is the model. So by understanding the system, you have to make a model. So as I told you, it is generally a two-way approach. Sometimes what happens, sometimes the officially speaking or formally speaking, every designer should first have a model and then they can go for implementation. But in industry that does not happen always that way. So this is a hybrid kind of approach. You implement something, you model something, because finally implementation, always deadlines are there. So just as we are doing in our BTech life, same thing people also are doing in the industry in a slightly quote unquote similar manner. They also have deadlines to meet. So when deadlines come, they do not exactly go for real kind of modeling, they exactly try to fix up something and implement and bring it to the market. This is a real fact, but means this also should be taken with a quote unquote pinch of salt, because you cannot say that it is universally true, but for many cases it actually happens that way. So basically that is what happens after everything is product has been made, people or in the final stages of design, this verification team basically understands the design and they make a formal modeling out of it. That is the Kripke structure. Then there is something called specification, that is the formula. In all paths globally this should happen. So what should happen basically, you have to write in terms of formula. Like for example, if you say that you have designed a printer, then you have to write for all paths globally, whenever a request goes in future, grant should be accepted. So that way you write your design intent in terms of specification. And then there is something called a model checking algorithm, which will try to find out in which states the formula is valid and which state is not valid. So in fact, if you are giving some kind of specification to be checked, there should not be any states in the system where the first specification is invalid. If this is invalid, that is actually a counter example, and you have to verify what has gone wrong. In this case what happened, we were doing it manually. Okay, so in this path it is not satisfied, in this path it is not satisfied, in this path it is satisfied. So we are saying that okay, G is existential, so it is true. But if it is a large system, of course you can never do it manually. So that is actually the idea of model checking, which will automatically do this labeling for you. So now we are going to see model checking is basically something called CTL model checking is something called labeling algorithm, which we will now look at. So basically what it does, it takes a CTL model M and it takes a formula phi, and output is the set of states where satisfy phi. So generally your formula should be satisfied in all the states, and whichever state it is not satisfying, it will give a counter example that you can go for and debug it. So basically there are a lot of CTL formulas can be there, but generally all paths in future, there exists a path until and there exists a path x. So basically this is an adequate set of operators for CTL. Any other CTL formula can be represented in terms of this. So as I told you, in this lecture we are trying to put everything together in a nutshell. We are not going to show the proofs, etc. You can look at any standard textbook on model checking, which will tell. But these are the three most fundamental fundamental temporal operators for CTL. You can write any CTL formula using this. So in this lecture we will see how the modeling or model checking is done on this basic adequate set of temporal operators. So atomic proposition already told you to P. So if some states you have to find out whether the atomic proposition is valid or not, it is just simply you check whether on the state whether the labeling is with P or not. Logical connectors are very easy to check, that is if you say in all the states P and Q should be valid. So you have to find out in both the states the labeling of P and Q should be there. Now we are going to see when we are going to real temporal business, that is there exists a path where in next state P is true. How do you actually do it? Label any state x with Px, the algorithm is label any state with exp if at least one of its successors is labeled with P. That means if there is a state x and maybe assume that there is another state here, maybe many paths may be there, here at least it is marked with P. Then you can easily mark this as exp. And you have to keep on doing it until there is no other change. That means the model is there, you have to browse through or you have to traverse the entire graph, and basically if you find out that there is any state where P is true, the back state you have to mark it as exp, and you have to keep on doing it until there is no more change, or in fact you have to traverse the entire graph and you have to do it. Now complexity comes in. So if you can find, you already know from finite automata theory that if the number of state variables is n, the number of states in the model can be 2 to the power n. So if your system has 100 variables, the state model or the formal model on which you will do this label or model checking will be 2 to the power 100. No way you can achieve it. So what we are going to see today basically is that modeling checking generally we are going to see, but along with it also we have to appreciate the fact that with a very large system you cannot have an explicit state modeling on which you have to do the verification. So if the model itself is not there, I don't know where you will do the verification. So all the future lectures we will try to see how we can reduce the modeling or the model itself, so that you can do verification on the reduced model. So we will see binary decision diagrams, we will see arithmetic decision diagrams and so forth. Right? So that modeling is very simple. So if there is some state exp is done in this manner. So graph is there, if some state p is there, the beforehand state or the root state, the predecessor state you can mark as exp. Now, so this is an example. So that is next state. Now another example we are looking at EFP. So the three ones we are taking. So EX and then EF. So although EF is not a part of this, but still we are just giving it an example. So, okay, sorry, basically it is EX, I should not have written it as this one, I should have written it as EXP, sorry. We need not talk at all about EFP because it can be represented using other properties. So how do you do it? So in this case, P is there. So you browse this whole graph and you can find out that the predecessor state is S7 and S1. So very easily you can write EXP here, EXP here, and your basically job is done. So only in these two states basically you can see the next state the property P is true. So that is actually a model checking. So if somebody says that EXP has to be this very important property and it should be valid in all these states, then you will say that only in S1 and S7 it is valid and in no other state it is valid basically. That is your counter example. See what has to be changed to make the design proper. Okay. So we write it, this is the formal way of writing the algorithm. So sat P, that is satisfiability of P, that means in whichever states P is true, that you have to mark. So sat of P means only in S4 P is true, that is equal to state set X, and what state has to be labeled? Some transition S0 to S1, and in S1 basically X is true. That is nothing but here this property is true, so this one has to be labeled. So basically if you look at it, so X is somewhere where P is true and you have to make set Y which is nothing but all states S0 such that there is a transition from S0 to S1, and in S1 basically P is true. That is saying something like S0 to S1. In S1 we already know P is true, and by this SAT formula then this one you have to label it that EX. Simple way of doing it. This is the algorithm way of writing it. Now in all paths in future. So we are going to take AF now. So how to do it? In this case it says in all paths in future P has to be true. So and we always again I want to highlight this fact that present is future. So if I say that here P is true, you can write that this state satisfies AFP. That means present is future. So in future it may be true, but if in the present state itself P is true, that means it is valid. So basically what do we write? The algorithm is if any state S is labeled with P, label it with AFP. As I told you, present is future. And repeat, label any state AF with P if all its successor states are labeled with AFP until no change. I will show you an example. The formula is P. If P holds in the state itself is true, you just label it, or AX AFP, that is all states next, all paths in future pre. So then is a way of labeling. Let us not go too much into formalism, you can easily understand after I show you the example. So wherever P is true, you make AFP true, AFP true, AFP true. Then basically you put it this way. That is, now you see here all the states from here it is labeled with AFP, AFP, AFP. Assuming this is assumed to be a situation with the leaf nodes, so only P is there, so I am making it with P, AFP. Now you can see I can also mark it with AFP because all the paths here AFP is true. So in this case you will find out that this one AFP is true over here, and similarly on this case until there is no change or we reach a fixed point. Now we will go for the temporal operator. So by doing it actually tell the same thing. If some state is labeled with this, mark with AFP. Label any state with AFP if all successor states are labeled with AFP until there is no change. So if there is P, just do it because present is future. So even if there are all paths, any paths are there, it can happen also, but I can still mark it in all paths in future true because present it has been true over here. So even if nowhere P is true in sequence, I do not bother because present it has been true. So I will mark it as AFP, and then finally we can also make it because all the predecessor nodes are marked with AFP. Done. So that way you can do the modeling. Secondly, this is there exists P until Q. So how will you do it? If any state S is labeled with Q, label it with there exists P until Q, because here Q is the safety. It says that P should hold until Q starts holding. So if somewhere Q starts holding, you definitely put it. Then similarly label any states with this if it is equal with P and at least one of its successor is labeled with this until no change. Okay, always better to show the figure. So here Q is equal to true. So if Q is equal to true, that means basically you can directly write E equal to there exists a path where P until Q, because here Q has become true. So you need not think about at least even P over here because Q is starting to be true in this case. Then what it says, there at least from this place P is true first of all, and there exists at least one path because we are looking at the existential quantification. So at least one path where P until Q is true. So there also you can put it is P until Q and you are labeling. You have to keep on doing it and a fixed point is reached or there is no change. Fixed point is there is no change. So basically that is nothing but if you read it, it will be this. Label any state with Q, label it P until Q, that already you have done in the first case. Label any state with P until Q if it is labeled with P and at least one of its successor is labeled with this. So that is P is there and this state is already labeled with E P until Q. So we have done this. right. This is the algorithm. I am not going to go for that. What I have told you is written in this pseudocode. Now, one more we are going to see. So, we have seen how many? So, we have seen basically AF, EU and EX. Okay. One more we are just going to just see this one. This may not be AG. AGP is not actually a part of this basic set, but still just we are going to give you an example. That means the idea is that for any operator you take like E, P until Q or AF, for every such formula the way of labeling algorithm will be different. But actually why we have discussed mainly for these three, because any property you write can be represented in these terms. You have to modify them in these terms and you can write. But it does not mean that if there is some temporal operator like this one AGP which does not follow to the basic set, cannot be model checked. They can also be model checked and there will be a different model labeling algorithm. So, any temporal operator you take in CTL, there will be a different model checking or labeling algorithm. You can use them to do it, but in this case we have first limited to the preliminary basic three ones, because like AGP can also be written in terms of these three basic operators. But still, just to for the sake of completeness, basically I am also going to show you that even though this is not a part of the basic set, still how to go for a model checking for this. In fact, we always write different type of CTL properties and we do not always try to model them in terms of the basic ones. No, we do not do that. We try to keep it in the natural form. Like also we can use something which is non-basic and we can have we have different model checking rules for them and we can do it. But as I told that this is a compressed lecture, so in this case we have tried to slightly deviate a bit and we have mainly shown for the three basic operators, and as a slight offshoot I am also going to show that even though it is not a basic operator, but still how to go for a model checking for this and the algorithm will be slightly different. It is saying at AGP there is all paths globally P, that means everywhere P should be true. How to do that? So, first you label all states with AGP true. You just forget whether P is there or not, you remove it. If any state is not labeled with P, delete AGP and keep on doing it. Delete the label AGP from any state if all its successors are not labeled AGP and there is no change. It is very simple, like first you label all the steps with AGP and then start removing where you have made a mistake. This is slightly different way of model checking. The algorithm is slightly different compared to the other three. Other three basically we were adding up the labels, here we are deleting the labels. So, for example, if you look at it, so in this case here P and P will be true. So, directly we will write here AGP and then you have to keep on deleting it. So, you will find out that in this case if you look at it, I will do it in all these states basically, just I am just giving the example, I will do it all the states AGP, but in this case you see in this AGP. So, from here all paths globally P has to be true. Now, you see look at it, here P is not true. So, obviously I have to delete this. Similarly, all paths will have AGP and everywhere it will be deleted, because there will be at least some states in future where AGP is not, P is not there or AGP is not true in that case. But if you look at these states specially, sorry there should be a loop over here, they forgot to draw. So, in this case if you look at it, so there is a self loop over here. So, in this case if P is true, the successor is only P, S5 is the successor of itself, only state which is successor which is AGP is true. So, this state AGP will be true over here. That means in this state all paths globally P is true because it is a self loop over here. So, in fact, what we have done, all the states were first labeled with AGP including this, and then we will find out that there is a path like for example. So, in this case you find out that this is the state successor with where AGP is true is not labeled because P is not true over here, I will delete it. Similarly, all the states the label will go, only the remaining here will be there because it is a self loop and AGP is true over here. Done. So, now we are coming to practical examples. So, lot of stray examples, abstract example, P, Q, R state machines we have given. Now, basically we are coming to a practical example of a microwave oven control and see how basically CTL model checking is applicable over here. So, it says specification, design of a controller, door of the microwave are either open or closed, start the oven, reset. That means the door can be open and closed, there will be heating and non-heating and some reset and some designs will be there. Like we know in a modern microwave what we do, we have to place something, close the door, put it, it will be heating up and then actually we will stop it, open the door and. But one thing has to be it is very much important, you have to remember that one very important thing, that when the door is open, you cannot have the heating on. That is a critical catastrophe will happen, that micro radiations will come out if the door is open and your heating is on. So, that has to not be there. So, this is basically your model. So, again if you can see there are some variables and like start, close, heat and error. Start means on, close means door closed, heat means microwave is on, error is some variable. So 4 variables means 2 to the power 4, 16 possible combinations are there. And if I make an explicit enumeration, you can find out this will be a huge state space. That is where actually the complexity is going to kill you. So in all the optimization lectures, basically we will see that how to handle these complexities by not explicitly representing with the explicit state space model. But anyway, in this lecture we are not going for optimization, we are just trying the basics. So we are going to see how model checking is basically done on this microwave control. So it is saying first it is not start, not close means door is open, not heat, oven is off, not error. There is no error, is off and the door is closed. Not closed means door is open, door is basically open. Then if you can look at it here, you can find out something interesting, that it says door closed means the close will be true, door open means it will be true. Now if you see what is the flow, so first you will close the door, then you will start the oven. So basically start was not start, it has become start, right. Then it will be warming up, that means heating is on. Then basically cooking means when heating is on, it will go over here same state and it will be a looping because cooking is going on. Once it is done, you can find out, you can go over here, heating will be off and then again you can open the door. Or basically you can, while the cooking is also going on, you can directly open the door, which you always do in microwave oven, sometimes we do, but immediately at that point if you can see that it will become off, door if you open the door it will be off, heating will be off and the door is going to be open. That means this path basically if you look at it, cooking is going on, if I open the door it is going to be a automatic off, that is start, no start, open, no heat. So that is a safe condition. So this part actually if you see, this models the normal operation of a heat, your microwave. So this part also you can see, sometimes you can take this path or sometimes I can take, sometimes you always do it, heating microwave is going on, quickly want to have something, you open the door, bring it out. That means then you are going from here, or you can take the normal procedure, you say stop, heat will stop and then you can open the door, that is switch off and then open, or sometimes you can directly open. So anyway, but the safety feature is already given. Now the other part is basically an error part. So some error or beep will be given. So your door is not closed, that is open. So your door is open and you start the oven. So basically heating will not be there and it will give a beep. That is your door is open, you start switching on the heater. So it will say error, that means a beep will be given. And then what you can do is that basically in this case you can close the door and then you can again reset it. So you close the door, then automatically will be reset and you and basically you can start doing the normal heating point over. There is one way of doing it. So basically start the oven, the door was open, then basically you close the door, then automatically reset and you come to the normal track. Or again you can open and close the door, nothing is going to happen. So this part actually, this two part basically which I am going to look at it here, open, this is something like, it's a wrong way of operating the oven, but still it works with a beep. So for example, you might have kept the door open or slightly open, you don't know, start switching on for heating, so it will be a beep, then basically you close the door and then basically automatically reset and start your, basically oven will start. So you can easily look at it and you can easily interpret what I mean to say. Right now, two conditions to be checked. One is microwave should not heat up with its door closed, very important. Secondly, once we start the oven, eventually it should start heating. I will show both this specification how they have to be model checked. So what it is saying? First one is saying your microwave should not heat up when its door is open. So open means that is not closed and heat. This should not happen. So that means what? It is basically something like not off this. This condition is bad. Door is open, heat is done. So that is bad. So you should have a not of this and it should hold globally in all the states, AG. And the second property is saying that once we start the oven, eventually it should start heating. That means if we start it in all paths in future, it should start heating. That is something we all request for all machines. We switch it on, always in future, all the paths heat should start or the machine should give it. And it should happen in all paths globally. Now I will start doing the model checking. Again, first one is very, very simple. First one we are saying that not close and heat. That should not be true in a state. So if you can look at all the states, in no state it will be true. That is not close and heat. This is also not true over here because not close is true but not heat. So this combination like not close and heat, you will find out that it is not true in any of the states. That means first we will model check this. This is very simple. You traverse all the states and just check if any combination is there or not. So if this combination is not there, so this combination basically let me call it 5. So it will be 5, if I label it 5, 5. So in fact not phi will be true in all the cases. So in fact, I will not label it. So in none of these states this phi is going to be represented. That means in everywhere not phi is going to be true. So let me call this whole thing not phi as some psi. Not this one, that is the whole formula inside, I am calling it as psi. This whole thing I am calling as psi. So this one will be true over, so it will be true over all the states. Because nowhere this combination is true. This combination is true nowhere. Now all paths globally, we have already seen the labeling. So in fact, as all these states basically has the psi true, so AG psi will be labeled in all these states, and basically AG of psi is going to hold in all these states. So you will say that all these states basically satisfies this formula, and so this model is verified to be true for this. That means there is no state that is in this case, if the door is open, the micro is not going to be heated. So very good, safety is done. Now we are going to check for the more complex this thing, in which case we said that I put a start, this is very critical, put a start, and in future heat should be there. So what I have to do it in steps. So first I have to think about in which states heat is true, that is heat I have to first check. So if you look at it, you can find that heat is true in state S7 and S4 only. So S1 means heat, S1 and S4 it is true. So heat is true in this case. So I can write it as heat. So some heat is true over here, that is S1, right. Now all paths in future heat. So basically, so these are the two states I am marking, S4 and S7, which are true with heat. Now in all paths in future heat, which more state is there? If you look at it, I will do the same model checking algorithm for all paths in future, that labeling algorithm you have to do. If you do it, you will find out that S6 will be coming, all paths in future heat. So this one heat, so in all paths, so these are the two states where heat is there. So now I am saying all paths in future heat. So if you look at basically S4, so S4, right, just a minute. So S4 and S7, S1 is the initial condition. So these are the two states where heat is true. Now basically you see in which path, all paths in future. Now if you look at it, if you look at your state S6, so S6 there is only one path from here in which this is heat is true and heat is true over here. So from S6 there is all path, there is only one path here where in future heat is going to be true. So straight away S6 will enter this group. Now but you can easily appreciate that S3 will not go into the loop, because S3 has one more path which is looping over here where heat is not going to be true. So S3, S1 will not come into this group. Now so S4, S7 and S6. Now if you look at S4, so this S6 has come over here, S7 also will satisfy, because as I told you all paths in future is present also. So here automatically heat is true, so automatically S7 will be there, and here also heat is true. So by default, as heating is true in my parent state, automatically this will be there. So this is the only new state which is coming in. So all paths in future heat will be S4, S7 and S6. These are the two states by default, because they are home state for heat, and this is one more state is coming in because there is only one path from here where in future heat is going to be true. So finally all paths heat means these are the three states you should mark, this one and this one, where this is going to be true, right. So now in this case, so this one and this one are the three states where this is going to be true. Now I have to now check for start, where start is true. So start is true basically if you look at, so I will make a cross. So start is true over S4, S7, S6, S2 and S5. These are the states where basically start is going to be true. Now X imply D. So now these states where is very important, but in this S2 and S4 this AF heat is going to be false. So in these are the two states where AF heat is false, S2 and S5 AF heat is false. Now as I told you, there is something called vacuous business. So these three states obviously this is going to be true, because start, that is start implies AF heat. So this one is true, implies this one is true, implies this one is true, implies this. So of course in these three states S4, S7 and S6 you will find that start implies AF true is holding. So I am making a chunk. Now in this S2 and S5 if you look, start is true but AF heat is false. So A implies B, B is false. So definitely in these states basically this formula, this whole thing is not going to be true. It is something like A imply B and B is false, A is true. So therefore, this whole formula is not valid in state S5 and S2 and S5. Importantly, now let us think about S1 and S3. Very interesting. Here start is false. Here also start is false. That means this one is going, these two basically is making this formula true vacuously, because in these states start is false. So vacuously it is true. So A imply B. So if A is false itself, we think that the false statement is true vacuously. So we will have something like this, so this is what is the steps. So by labeling, so it will find out that S4, S7, S6, S3 and S1. So these are the states where this is actually true. Now, so what I have done it manually, that this is vacuously true over here, not this, that, but in fact basically you have to do it by model checking already. So already I have told you that for all things like A imply B, all other cases there will be different ways of labeling and doing the model checking. So in fact we have shown only for the basic ones, but for all there will be a model checking method, algorithms will be there. But what I have done manually, the labeling will be done using an automated algorithm. But still now we are somewhere where it says that start heat S4, S7, S6, S4, S7, S6 and S3 and S1. So this is the set of states where this one is true. Now it says that all paths globally. So of course, if you look at it, if you look at the last statement, what it says that here, let us call it, this whole thing, let me call it as K. So here this property is K is true over this thing. Now it is saying all paths globally, this should hold. Now already we have seen how to do that labeling. So all the states will put all paths globally, and then we will start eliminating states from which some paths will be there where this formula is false. So everywhere we will start putting AGK you will start writing, AGK, all the states you will write. Even in these states also you will start writing. Right now, sorry. We will write, but then we will delete it basically because K or this statements is not true over here. Of course, AGK it will be there, but then you will remove it. So that will go over these states because there is some paths over here in which fact it is not actually holding. So just by the model checking algorithm, AGK will be eliminated. K is nothing but this formula. But now you see state S1, there is at least a path now here where here in this case AG5 is not labeled. So immediately this one also will start going off. Similarly, if you look at it, this one will be gone, right? This state is gone. No, so now there will be another state here where this formula is not holding. So again this one will go off, right? Then basically if you look at it, now this state if you see there is one path over here where this K is not there, K has been eliminated. So this labeling will also get removed. Now by virtue this has been removed, so this one will also get removed. Similarly, when this gets removed, this one will get removed. So slowly we will find out by steps that all these paths are gone and finally you will land up in nothing. So initially we will have these states, but these states will also have the label, then this one will get this labeling AG label AGK, AGK will also be there, they will be getting eliminated because K is false over here. Then this one will lose its label because this is not there, then as S1 will lose the label, then S3 will also lose the label. Similarly, when S3 will lose the label, S4 will lose the label, then S7, then S6 and finally it will be a null set. So null set means none of these states will actually satisfy this formula. So you have generated a counter example that what is the case, start and in future hit, what is the problem. So here it is very interesting. In this case, this example actually has given you to model a system. It has shown you how to model a system, how to write some temporal CTL formula that you want to verify what it happens, and then we have to see how we do model checking, and then we find out states where it is violating. So now it says that something has been violated. Now we have to debug what is the problem. First thing is that whether this modeling is wrong, that is one question. Secondly, whether this formula I have written is wrong. So many things can go error. Of course, the model checking algorithm is assumed to be proper and it is known to be correct. So there is no problem in the way we are doing the modeling. It is model checking. So the labeling and these properties are already known, proved to be correct. So that is no problem there. So now what to do? So first I will check whether the modeling is proper or not. So in fact, the way we have discussed, you have to appreciate the fact there is no problem in the modeling. The modeling is correct. Then what is the problem? Another way is that since somebody can tell me that way I have written the specification may also have an error. So this example slightly is a twisted example, because I could have also made the model error and shown that how to correct it, but without doing that you can also try in your home, but there I have tried to give a different flavor here. So what I have seen, I assuming that the property itself written is slightly a problem. What? It should write this one, all paths globally, start implies all paths in future heat, but not error. That means this is some part which was designed to have some error correction. So if there is an error, then I don't bother about it, because in the error case the heating is never on. So if the error is on, the heating is always off. So that I always know. So therefore I have to think, or in other case I have to always think that if the error is there, I don't bother the property. The property says that in fact start in future heat should be there, but it will hold if and only if the error is not blinking. If the error is blinking, then basically your heater will or microwave will never start. So your correct property should be something like start and not error implies all paths, that all paths in future heat and not error. That is, in the non-error errors environment it should hold. Now basically I am not going to do the elaborately, I discuss it. Same thing you have to do, only along with heat. It is first we started with this start. So in fact now with the start and error, so the states are S4 and S7. Then all paths in future, start and not error will be these states. Finally it will land up to the stable state S4, S6 and S7. Then again you will have to go for all paths in heat. Similar way you have to find out the labels for all paths in future heat and not label. So this is basically nothing but your S4, S6 and S7. So this way you are doing. Similarly you have to repeat for this one, you know, this state of states you know, you check for implication, and then finally you will verify the property as I have done. You will find out that it will be satisfying in all these states. That I am just showing, I have just shown in the slides. I am not elaborately discussing, because it is just a repetition. Just you look at this slide, I am just holding these slides for, the slides will also be uploaded, but you can just see for the time being. There are the steps, you do a manual calculation and you will find out that it is true in all the states. So therefore in this case was a stray example I had given, in which case I had made slightly erroneous your basically the specification. So this just give you a flavor that either there can be error in the specification, either there can be error in the model. Anyway, it is very rare that both of them or any one of them have some errors, but still your model checking means you are finding that all the properties are satisfied. Generally what happens, there is some errors in the model itself, because it is very complicated to build it. Specification generally a small way of representing what we want, so generally there is no bugs here, but anywhere, if anywhere there is a bug, it will be give you a error, and then you have to find out which has to be rectified. If the modeling has to be rectified, then there again can be two cases. Either the model is, while you are translating the system to model, there may be an error, so then you have to modify the model itself, or it may happen that the system itself had some bugs, which is generally you always want to catch. Then you can go and tell guys, see your this is a problem, this is the counterexample you change. So in fact in the formal model checking, the advantage is everything is done mathematically, so it is always exhaustive and guaranteed. So generally if it says that the model is satisfying the properties, then it is guaranteed that for all input cases and those properties model will behave properly. So that is the idea of formal verification over simulation based verification, etc. So this brings us to the end of this introductory lecture, and what we have to take from here. From here you have to understand the basics of CTL model checking. There is another way of doing it called LTL model checking, slight deviation, that you can easily go home and read. But what explicitly is the issue? The model. So for a microwave there are 4 variables, you can find out that 2 to the power for 16 states. For a very large system, 100 and 1000 of variables, you cannot even make the model itself. If you are not able to make the model itself, forget, just think how can you verify. So to handle larger systems, we will see how to optimize it, how you use binary addition diagrams to do it, then also we will see high level abstraction and so many other different ways like bounded model checking, etc. So this is how we will go in this module. Thank you.